Hello, in the first video we proved that there are three forms of solution to this general second order differential equation, which we call our complementary function, and the solutions we're going to have below using our auxiliary equation, and we had three forms of solution. So what I'm going to do in this video is just look at how we use this, what sort of situation, and what forms of solutions that we get for each of those, what it looks like graphically. Okay, here's the most classic example that we would use, damped harmonic motion. So what have I got here? Well, I've got some mass mg and it's hanging down from ceiling or some support. There's a spring attached to it and that has a force pulling upwards, and that's proportional to the extension of the spring. On the right hand side we have a damper and the force from that is going upwards, and that's proportional to the velocity. So what we're looking at here is like a wheel attached to a car, because that usually has a spring and damper to keep it under control and stop it bouncing around too much. So if I now use that setup in F equals ma, Newton's second law, well, my downward force is mg, the weight force. In resisting that is my damper force and my spring force, and the result of all of that is my mass times acceleration. Now I know that v equals dx by dt, because velocity is the rate of change of distance with respect to time, and I know that acceleration is d2x by dt squared. Yeah, that's the second differential of distance respect to time. If I rearrange that, I've now got a nice second order differential equation. Yeah, I've got all my x terms on the left hand side and I've got my mg on the right hand side. So if I wanted to solve this and I wanted to get my complementary function, I would treat this as being having nothing on the right hand side, so I'd set this equal to 0. I would differentiate and create my auxiliary function, my auxiliary equation, which is z squared plus 2z plus 4 equals 0, which has root z equals -1 plus or minus the square root of 3i. And I would write that as being e to the minus 1t, so that's my decay, exponential decay, and then a vibration here, an oscillation in terms of cos and sine with the frequency root 3. It's what we would be using for my omega, which would tell us what my frequency is. So that's how we use it a lot of the time. It turns up an awful lot in vibrations of structures of all sorts, and also in musical instruments like violin, strings, etc. Okay, so let's have a look at the different situations we've got. So let's look at my discriminant is greater than 0, so I have two real roots, lambda 1 and lambda 2. But let's look at what happens if we have different signs here. So if they're both positive, well, we're just looking at straightforward exponential increase, aren't we? So that makes our life easy. If one of them is positive and one of them is negative, well, it's going to go down first with the negative, and then it's going to then be dominated by the positive exponential, so that's going to grow and set off to infinity again, isn't it? So these are both heading off to infinity. And if both of my solutions are negative, then I've got exponential decay, haven't I? So it's going to go down to 0 at that point. So there's our three options we've got for two real roots. Okay, if our discriminant is less than 0, then we have two complex roots. We've got imaginary components, so we get some sort of exponential for the real component, and then we get an oscillation, a sine wave type setup for our imaginary component. So if lambda is greater than 0, so then this is going to be an exponential growth. Yeah, we're still going to have an oscillation for omega, but it will be an oscillation here where it's expanding in its magnitude. You can see this outer, I've put the red dashes there that sort of show you where the envelope is for the e to the lambda x, and you can see that the oscillation is just growing. Now if lambda is negative, then again I've got my oscillation, but this time my envelope is getting narrower, isn't it? So over time this is going to decay away and the vibration will stop. Yeah, so our vibration there in our, which is what usually happens in a, you'd want to happen in your cart wheel, isn't it? Support is you'd like the vibration to damp away to zero. Yeah. Okay, let's look at our third situation where we've got a repeated root. Now, this, we've got our exponential here, so that's going to be our dominant factor, isn't it? That if our exponential is lambda is greater than 0, in fact, if all of these factors are greater than 0, we're going to get exponential growth, and this is going to go off to infinity. It could go off to negative infinity, couldn't it, if the factors, if A and B were negative, it would go off to negative infinity, wouldn't it? But it's the B factor that dominates here. So if I had a lambda and an A that were positive and the B was negative, what would happen? Well, it would start going up because the A would dominate at first, and then it would go follow the BX term, and then it would be driven by the lambda, wouldn't it? So this one's setting off to negative infinity because our lambda is greater than 0 and our B is less than 0 is negative, so that's going to send it off to negative infinity. There we go. But if lambda is less than 0, well, we're an exponential decay, aren't we? So it's heading off to 0. It could go up a bit at first as the B term drives us up with increasing x, but then the exponential comes to dominate and brings it down. So there you have it, 3 sets of solutions, and we use it a lot in mechanics, etc., for vibrations.